Hi folks, we're going to take a look at number 14 on page 157. So here they tell us that we're working with a square-based box with no top, and they give us a specific volume it has to have. And they want us to determine the dimensions of the box that minimizes the amount of material used. So in other words, we want to minimize the surface area of this box because that's what's going to minimize the materials. Now, you might have noticed that I skipped this line here, and that's because it's not well written here. In fact, I think there's probably a word missing in this sentence, because it says if the smallest dimension is 5 centimeters, it almost makes it sound as though one of the dimensions has to be equal to 5 centimeters. But I think what they meant to say is if the smallest possible dimension is 5 centimeters, meaning neither the length, width, or height can be smaller than 5 centimeters. Okay, so again, you could probably just add smallest possible dimension here to fix that. All right, so let's draw a diagram. So we've got a box. It's square base, so these two sides, the base and width are the same, and it's open top. So not a bad idea on your diagram to do something to indicate that, just so that you don't accidentally include it in your surface area. All right, so let's call the base and width X, and I'll call the height Y. All right, and let's come up with a model for the surface area. So the area is going to be, well, the area of the base, which is just going to be X squared. Okay, notice I'm not taking the top, plus, and each of the sides has the same area, X times Y, so plus 4X times Y. All right, but as is often the case, we have two variables in our model. So luckily we have this constraint here that the volume is 10,000 centimeters cubed. So the volume of this box is going to be given by the area of the base, so X squared times the height Y, and that's equal to 10,000. And so now, and I think I accidentally, 3/4, sorry, that's 100,000. So let's get rid of one of those zeros. I need to use this to write one variable in terms of the other. Now, which one to choose depends on what my equation looks like, and I see that I could solve for X squared, which would be great, but then I'd have to solve for X for that one, and I'd end up with a square root. So I want to avoid that at all costs if I can, so it makes more sense to isolate the Y, and then I can just replace this into the equation much more easily. So 4X times 10,000 over X squared. Can do a little simplifying here. That X reduces with one of the X's in the denominator. And so now we have our model in terms of one variable. So that'll just be 40,000 over X. All right. So now let's see if we can figure out the domain here. Well, it says that dimension has to be bigger than or equal to 5 centimeters. So I know that X has to be equal to, has to be larger than or equal to 5. Now the question is there an upper bound? You know, I mean, this base could get, bigger and bigger and bigger and bigger. The problem is that as the X gets larger, the Y gets smaller. And remember what it said. It says the smallest dimension can at most be, or at least has to be 5 centimeters. Okay, so I think what I should do is calculate what the X value is when the Y value is at its smallest possible value, which is 5. Because the smaller Y is, the bigger X is. Okay, so here if I calculate X when Y is equal to 5, so here I've got my 10,000 over, so I'm going to be dividing by Y, which is 5, and then taking the square root. And let's figure out what the, we'll call this X max is. Okay. So here, okay, so we've got 10,000 divided by 5, okay, and exponent 0.5, okay, so 44.7, more or less. Okay, so that means here X has to be bigger than or equal to 5, and then less than or equal to, well, I guess I'll put the exact value there, the square root of 2,000, which is about 44.7. All right, so we are working on a closed interval. Although, as you'll see, I'm going to make a comment about this later on, because this is not necessarily the most obvious thing to do, especially if you're, trying to do this quickly. So I'm going to make a comment about that later on. Okay, so for now, let's just do what we normally do. Let's take the derivative. Okay, so here we have 2x, and then here for 40,000 times x to the negative 1. So that's going to be negative 1. So negative 40,000 times x to the negative 2. So that's going to go into the denominator as x squared. Okay, and we're going to make this equal to 0. So let's multiply both sides by x squared. So here this is going to become 2x cubed minus 40,000. And that's still equal to 0. And so x is just going to be equal to the cube root. If I solve this, bring the 40,000 to the other side, divided by 2. Of course, that's just going to be 20,000. Okay, so let's see what that gives us and make sure that it's in our domain. Okay, so here we've got 40,000, just to be sure, divided by 2. Don't take any chances. Exponent 1/3, and that gives us 27.1. Okay. Now, let me talk about what I was saying before. Let's say you're not seeing, whether this, you're not seeing what the maximum value would be here for the x. I would just suggest do the problem and see where it takes you. Okay, so don't get hung up on the domain. I mean, if it turns out, now the idea here is that had this not been in this domain, it means the minimum would have occurred at one of the endpoints. Okay, like for example, let's say the x value that was going to give you the minimum would have resulted in a y value that was less than 5, which you would have found out at a certain point. Just don't give up on the problem because you can't calculate the domain. In this case here, it's going to end up working out because it may work out depending on how the function behaves near this critical point. So let's test that out. So from 5 to, about 44.7, and we're testing at 27.1. Okay. So let's take, I don't know, something easy like 10, and here let's take 30. All right, so let's test the intervals. Okay, so what do we have? Where's my derivative? My derivative is here. So I've got 2 times 10, so 20 minus 40,000 divided by 10 squared, 100. And I have something negative, and then here we've got, where is it here? 2x, so that's going to be 60 minus 40,000 divided by 30 squared, okay, and we see we have something that's positive, okay. Now, let's say we didn't, so you'll notice that I'm not testing the endpoints. I'm going to do it in our traditional way on a closed interval, testing all the endpoints. But this is just to show you that even if you hadn't gotten to the point where you found it, do as much as you can. And we see here that we can make the argument that between 5 and 27.1, it's continually decreasing to the local minimum, and then it's continually increasing. All right. Now, of course, the problem would have been if this maximum value for x was something less than 27, in which case that wouldn't have been the absolute minimum. Okay, but at least you would have solved most of the problem. Now, given that we did find the correct domain, what you could do now is just test the area at these 3 points. So test the area at 5, test the area at 44.7, and then test the area at 27.1. Okay. And I think, hopefully we will find that this is the one that's going to be the smallest. Okay, so let's do that quickly here from our area. So let's put in 5. We have 5 squared, so 25 plus 40,000 divided by 5. Oops, 5. Okay, and we have 8025. Let's test the other endpoint. So we have 44.7 squared plus 40,000 divided by 44.7 is equal to 2893. So significantly smaller. Okay, and now let's test 27.1. So 27.1 is going to be 27.1 squared plus 40,000 divided by 27.1, and we have 2210. So that is the smallest. Okay, we had actually already determined this before, but like I said, it could have been that this ending value here might have been something smaller than 27.1. So to do this problem 100% correctly, you want to be able to find the actual domain on which we're solving the problem. Here, let's take a look at what they're looking for. Determine the dimensions. So the dimensions, well, we already figured out that the x value was equal to 27.1. So x equals 27.1 centimeters. And so our y, or our height, is just going to be 10,000 over 27.1 squared. Okay, and that's from this equation here. So what do we have? 10,000 divided by 27.1 squared, and that gives us 13.6. Okay, which is larger than 5. All right, so just to do a recap on this one, because this was a bit of an interesting one. So step one was to get our model in terms of one variable. Where we needed to do a bit of work was to incorporate this idea that no dimension could be smaller than 5. So I knew x had to be greater than or equal to 5, but then I had to figure out the maximum value by using 5 as the minimum height value. Once I did that, take the derivative, check my endpoints and my critical points, get my answer. All right, that's it for this one.